G'day, in this video we're going to be looking at magnetism, in particular qualitative aspects of the magnetism topic. So in this video we'll be covering dot point 4, point 3, point 1, 2, 4 and 5. It's the final inquiry question for module 4 about electricity and magnetism. And the inquiry question states, how do magnetized and magnetic objects interact? The dot points covered in this video focus on some of the qualitative aspects that describe magnetized and magnetic objects and the way that they are able to interact with each other and the world. So our key learning intentions today are to first explore materials which are magnetic or interact with other magnetic fields. We call these ferromagnetic materials. We're going to explore how magnetic fields actually form, as well as how ferromagnetic materials can actually become permanent magnets. Once we have a bit more of an understanding of ferromagnetic materials, their magnetic field that they generate, and how they can actually be made to be permanent magnets to begin with, we'll then look at how magnetic materials can interact and how magnetic materials interact in magnetic fields. Importantly as well, we'll look at wires and solenoids, which generate a magnetic field through the flow of electrons in a current. First off, let's focus on magnetic materials. So commonly iron, nickel, and cobalt, primarily iron, are materials which have magnetic qualities that can produce a magnetic field or interact with a magnetic field. These are ferromagnetic materials. So importantly, these ferromagnetic materials, again, can be attracted to a magnetic field and can become magnetic themselves, meaning that they produce a magnetic field. The way in which ferromagnetic materials generate magnetic fields is actually quite a complex process. I'm going to be giving a really brief and generalized outline of how this works. The details are not extremely important to understand, but somewhat of an idea would be helpful. We're much more concerned in this topic about looking at how to apply the concept of ferromagnetism and magnetic field lines to interactions, rather than how the magnetic fields actually come to be to begin with. One of the most important concepts to understand for the generation of magnetic fields is that magnetic fields are generated by electrons, either by electron movement or by what we call electron spin that exists in electrons in atoms. Spin is not what we would assume in the traditional sense. We're not talking about the geometric turning of the electron itself, but it is a term which appears when we start to talk about quantum particles, and is a topic that we'll unpack in much more detail at the very end of this entire physics course. But for the moment, know that electrons can either have what we call an upspin or a downspin. They're kind of the opposites of each other. And the spins of these electrons are capable of being able to generate a magnetic field. So our first assumption should be, well, if there's lots of electrons on lots of atoms, then they really should be all generating magnetic fields. And while this is true in a sense, a really important thing to note is that a lot of the time, electrons exist in orbital pairs. And in these pairs, each electron has an opposite spin. Because each pair of electrons has an opposite spin, they generate opposing magnetic fields, meaning that most electrons that exist in these pairs will actually have magnetic fields that they generate that cancel each other out. It's the unpaired electrons that exist on certain atoms which are capable of generating a net magnetic field on the atom. However, if you have several unpaired electrons in an atom, this can also lead to cancellation of fields as well. It's these key concepts that actually dictate why there are very few elements that we consider to be ferromagnetic. Because in most instances, while there are magnetic fields being generated by electrons on the atom, in most cases, these fields are ultimately being cancelled out by other magnetic fields generated by electrons. There is only a small subset of elements which are able to generate some form of net magnetic field on the atom. So let's say we have a material like iron, which is ferromagnetic. We will find that in a piece of iron, there are a lot of what we call ferromagnetic domains. These are small clusters of atoms that produce aligning magnetic fields. So this concept is being expressed in the diagram here at the bottom. Here we have a cluster of atoms where all of the fields align to point in this direction. But next to it, there are another cluster of atoms, a material, in which the magnetic field is pointing in this direction. Each of these zones, again, are called these ferromagnetic domains. And for the majority of materials, the majority of iron or nickel or cobalt, these domains are also randomly aligned. They point in all different directions, and ultimately they cancel themselves out. However, the fact that these magnetic fields exist and these domains exist do allow the materials to be able to interact with other larger magnetic fields. If we have a material that is magnetized, generally speaking, that would mean that we would have a permanent magnet. So say, for example, a bar magnet. These are ferromagnetic materials which have all of their domains aligned. All of the magnetic fields point in the same direction. And this is what gives it the capacity to either attract other materials, attract other permanent magnets, or potentially repel other permanent magnets. So if we have a ferromagnetic material, how can we go from this, where all of the domains are randomly aligned, that all the field lines are pointing in different directions and they end up cancelling each other out, meaning that they're not actually magnetized? How can we get from that to a material where all field lines are aligned in the same direction, all domains are aligned, meaning that we actually have a material which generates a net magnetic field? Well, the key answer to that is we need to apply a magnetic field to the ferromagnetic material. So for example, if I were to apply a magnetic field to some ferromagnetic material, then this would try and force all of the material that is inside to align with the magnetic field that is present. What that would then try and do is encourage all of these domains to point upwards and align in the same direction. However, this is easier said than done. If the material is solid, then there isn't a lot of ability for the atoms, or the atoms in particular domains, to move, reshape, and realign themselves to all point in the same direction as the external magnetic field. Generally speaking, to make permanent magnets, this works best when we have ferromagnetic material that is melted, as this allows free movement of the atoms that can then align with the field. So at that point, if we've got that melted down material, let's say we've got some melted iron, we apply a magnetic field externally. The atoms should then all be able to move and realign so that their field lines point in the same direction. And when it cools, that will then lock those atoms into place. They'll all be generating a magnetic field in the same direction. All of the domains are now aligned. This is something that we can do to produce permanent magnets, but is also how permanent magnets naturally occur. Essentially, materials which are released from the Earth in volcanic activity can, at least in some part, have domains aligned to meet or match the direction of the magnetic field of the Earth. Once it cools, all of those domains solidify in that aligned or near aligned position. And in some cases, this generates material which has permanent magnetism. So how do we demonstrate the fields produced by magnets? Well, it's quite similar to how we've shown field lines for other field forces. So we can draw curved lines with arrows showing the direction of the field. Fittingly, the field lines show the force which is placed on a magnetic north pole, or the positive end of the magnet. So in a similar way to how we show electric fields by producing an arrow which shows the direction that force would be applied to a positive charge, here the arrows show the force which would be applied to magnetic north pole, or the positive pole of the magnet. So in this diagram here, we see that the lines extend outwards from the north pole, because if we were to put a north pole in this region, another one, it would be repelled away from this area. And we have arrows coming into the south pole, because if we put a north pole down the bottom here, we would expect it to be attracted to this area. Just like how we have charges where like charges repel and unlike charges attract to each other. Something to note on this diagram here that I liked is it highlights that the spacing between field lines can indicate magnetic field strength. If you have smaller spacing and more magnetic field lines, then this indicates a stronger field. Permanent magnets are not the only things that generate magnetic fields though. In fact, the flowing current in wires also does the same thing. If we go back to one of the first points that I raised in this video, magnetic fields are generated by electron movement, and that is exactly what an electric current is. It's the movement of electrons. This in turn generates a magnetic field. So when we have current flowing through a wire, field lines make a circular shape around the wire, and this is perpendicular to the direction of the current. This is what's being displayed in this picture here. However, if we are talking about this idea of field lines moving in a circle perpendicular to the direction of current, we're now trying to demonstrate a three-dimensional concept. we have current moving in one direction, and then the magnetic field lines, let's say that that's on our x-axis, and the magnetic field lines then existing on the xz plane. Therefore, to be able to draw this in 2 dimensions, we're going to have to use some conventions to be able to demonstrate third dimension. You'll notice here that the wire in this diagram is an orange circle, or more accurately, an orange circle with a dot in the center. What this is telling us, according to the key on the side, is that current is moving out of the page. And this is a convention that I wanted to unpack here because it's not something that we spent too much time on yet in this course. We are able to draw vectors, or more specifically current, that's moving into a page or out of a page to introduce the third dimension to a 2-dimensional diagram. So if we have vectors or current that are moving into the page, they are marked with a cross, and vectors or current that is moving out of the page is marked with a dot. The way to visualize this is what we would see for an arrow either moving and puncturing into a page, or an arrow which is puncturing and moving out of the page towards us. If we hold a page up in front of us and there is an arrow that punctures the page and is moving towards our faces, we won't see, at least to begin with, the feathers at the back of the arrow, but rather the arrow point. And that is shown like the dots here in this little key that we have. On the flip side, if we were to hold a page in front of our face and an arrow was to go past our face, past our head, into the page and away from us, what we would see is not the arrow head, but rather the feathers at the back, which are shown by this cross. Note that when we draw vectors generally, we either use the dot or the cross key. However, if we're looking at current, a lot of the time we will show this with a dot and cross, but also a circle around the outside, and that is to represent the wire that is carrying the current either into the page or out of the page. Keep in mind that when we are talking about current, the direction of current shows the direction that the positive charge would flow rather than the flow of negative electrons. While this might be a little bit counterintuitive because when we're talking about current, we are talking about the flow of electrons, it is consistent with other rules that we have talked about before with charge, where we always say that the direction of the arrow or the positive direction matches the behavior of positive charges rather than negative charges. So just to summarize, if you see an arrow that is showing current, it is showing you the direction of where positive charge would go, which is the opposite of the direction of electron flow. So something that I also want to introduce today is this idea of the right-hand grip rule, which helps to describe the direction that the magnetic field will circulate around a wire as current is flowing. So if you hold your hand out and you curl your 4 fingers and hold your thumb at a right angle to them, your thumb should represent the direction of current flow. Again, not the flow of electrons, but the flow of current or the flow of positive charge through the wire. And the curl of your fingers, your 4 fingertips, will point in the direction of the magnetic field. So for this example, and try this with me, if you were to hold your hand in front of the screen with your thumb pointing towards you, meaning that current is coming out of the page, and you curl your other 4 fingers of your right hand, you should see that your fingers follow the same direction as the field line shown in the diagram. Your fingertips are pointing hopefully downwards at this stage, which matches the curve that we see here in these parts of the diagram. Your fingers should be showing that same curve. This concept's a little bit tricky to sort of communicate through a PowerPoint, so it's a concept that we'll be looking at, making sure that we really understand quite well in our class time. Finally, I want to talk briefly about magnetic fields which are generated by solenoids. Essentially, a solenoid is a wire that is wrapped around and around and around and around, making a big coil of wires which can produce a larger magnetic field because you have lots and lots and lots of circles like we have here stacked on top of each other, each producing their own magnetic field. So our solenoid with all of the coils in the wire, again, will produce a larger magnetic field because each wire or each part of the wire is contributing to a larger generation of a magnetic field. So again, these field lines essentially are a circle around the wire. They're perpendicular to the direction of the current. So in this example here where we've only got one loop, if we've got current flowing in this direction and we use our right hand grip rule to match the direction of the current, we should see with our fingers that the magnetic field will move up through the inside of the loop and then proceed downwards as the magnetic field loops around the external parts of the looped wire. Similar principles can be applied when we start looking at solenoids, and essentially what that will mean is that there is a lot of magnetic field that's being funneled through the center of the solenoid all in one direction. And then in the external parts of the solenoid, we will find that the magnetic field runs in the opposite direction but meets up back at the end. Essentially, the field lines that we can see here quite closely match the behavior of bar magnets, and thus solenoids behave quite similarly to a conventional bar magnet. Lastly, I just want to show you some field lines that show magnetic field interactions. What we see here should be extremely similar to what we've already seen and talked about before when we look at the field lines for electrostatic particles. The main thing to remember is that opposite ends of a permanent magnet will attract. The north pole will pull in towards the south pole and vice versa. And that when we have like poles on our magnets being aligned with each other, they will repel each other and push each other away. We can see the same thing or the same principle when we put together ends of a bar magnet rather than lining the magnets up. Thank you very much, everyone. In the next video, we will conclude Module 4 and the Year 11 component of the course by focusing on magnetism and the two equations which quantitatively describe a lot of the concepts which I have covered today. But until then, have a good one.